In this video, we're going to be talking about information theory and getting a good introduction to some important terms that we're gonna need to know um, when it comes to information theory. So, what is information theory? It's the idea of like asking the question, how much information does a message carry? Does the details of an event tell you? If I tell you some information, if I tell you a message, how much did you just learn? How much did I reduce your uncertainty? That is what information theory is all about. And it's a pretty cool idea because we're kind of mathematically defining tools to do something that usually is like an intuitive thing. Like you would hear something like, oh, that gave me a lot of information, but it's hard to quantify. We're gonna kind of put in the work to actually do um, this quantifying. So the first thing I'll give you is like, okay, let's say I tell you, I'm gonna tell you two pieces of information. So my first fact is it is snowing in um, it is snowing in the Sahara, right? And the second fact is it is snowing in Antarctica. Okay? Which one of these did you gain more information from? Well, it's important to realize that one of these is more surprising than the other, and surprise is directly correlated with information. So, which one of these is more surprising? This one has a much higher surprise, right? Because the surprise is higher, that also means that the information in this message is higher, right? If I tell you it's snowing in Antarctica, it's low surprise. You're not surprised by that at all, so it doesn't give you any new information. It's kind of like, oh yeah, I expected that. I know it snows in Antarctica, no big deal, right? Another example is if I tell you like a mind-boggling fun fact, like, I don't know, um, ants can carry up to 400 times their weight or whatever. You hear it the first time, right? It surprises you, right? It's surprising, like, oh wow, I didn't know that, right? That means you gained information, right? You gained information from that message. But if I tell you it a second time right after, it's less surprising, and so you've gained less information, right? Probably none, because it's not surprising to you at all, right? You knew exactly what I was going to tell you. Okay, so now the thing is, we want to be able to get to a little bit more quantifying, a little bit more like mathematical. So we know the surprise of an event is actually related to its probability, right? If the probability of an event is high, then its surprise is low, right? Its surprise is actually, we can think of it as an inverse relationship and say that surprise is 1 over the probability. And we'll do that in a second. But just think about it, an event with high probability, I don't know, the sun coming out the next day, it doesn't surprise you, right? Because it happens every day, no surprise. So low information as well, right? And then vice versa, right? If you have an event with low probability, very surprising, like something that doesn't happen often, very surprising, lots of information. So the key, the key equation we're going to get at for information is that the information of some event E, okay, is equal to the log base 2 of 1 over p. So first of all, ignore the log for now. Just look at 1 over p, right? P is the probability of that event happening, right? And 1 over p would be the surprise, right? The lower the p, the bigger the surprise. The higher the probability, the lower the surprise, and thus the lower the information. So this part we understand, right? Now, why do we do log? Why do we deal with logs? We'll see that in a little bit. But first, let's like try and test this formula out, right? What if I have an information? What if I have an event? If I have an event with probability equal 1, right? I know it's guaranteed to happen. Well, we plug that in and we get that becomes log base 2 of 1 over 1, which is 1, which is 0 for our information, right? So an event that is guaranteed to happen has no information when it happens because you know it's going to happen. It's a probability of 1, right? In the same way, a probability of 0 where, we usually, let's not say 0 because then the 1 over 0 is undefined, but let's say like a very, very small number, right? that means we're going to be taking log base 2 of 1 over a small number is going to be a very big number, right? I don't know how many zeros, whatever, right? And so your information is going to be larger, right? So the lower the probability, the more the information, okay? Now, we're using log base 2 here, and that ensures that our information is measured in bits. So the unit of information when we use log base 2 is bits, okay? The way we define a bit is the amount of information you gain by learning the answer to a yes/no question. So like if you're flipping a coin, right? If you're flipping a coin, the possible outcomes are heads or tails, right? You can ask the question, is it heads? Correct? And when you find out that information, right, based on your question, you've gained 1 bit of information. So it's the amount of information that you gain, right? 1 bit is the amount of information you gain by figuring out the answer to a yes/no question, pretty much, right? 2 possible outcomes, binary. That's also why we use log base 2. Okay. The reason why we use, I'm going to clear the screen. Why do we use logarithm in general? The reason why is because one big reason is that we want information to be additive, in the sense that let's say we do 2 things. Let's say we flip a coin and then roll a dice. So we do these 2 events, okay? And we're going to assume they're independent. We would want, let's call the information associated with flipping a coin I flip, and this is I roll, okay? We would want the information of flipping a coin and then rolling a dice, correct, to be equal to the information of flipping plus the information of rolling the dice. That's what we would want, right? We don't want, like, it should just be, okay, I did them 2, they're independent, I should be able to add up their informations, right? And let's do an example, right? Let's say we get a heads and then we roll 3. Okay? The probability of getting a heads is 1/2. The probability of rolling a 3 is 1/6. So the total probability of getting heads and rolling a 3 is 1/12. Right? Now if we find the information associated with that, right, we can say information is going to be, oh, by the way, I wrote the formula for information before as information equals log base 2 of 1 over p, right? Based on log rules, we can rewrite this as negative log base 2 of p. So this is more commonly used just because you don't have a fraction inside. So let's write it like that. So information is negative log base 2 of 1/12, right? Now, the nice thing about using logs is that this thing can be split up. We can say the information associated, so the information associated with getting a heads and a 3 is equal to, well, why don't we split up this log? It turns into negative log base 2 of 1/2 minus log base 2 of 1/6, right? Based on the fact that, multiplication inside of logarithm can be split up into addition, right? And then, right, you can see that this right here is the information. So this is the total information. This is the information from the flip added to the information from the roll. So it works out nicely in the sense that our logarithms turn multiplication into addition, which is why they ensure that for independent events, the information is add. Okay. So this is the introduction to information. In the next video, we'll talk about entropy, which is like the second most important thing. So definitely check out the second video right after this.